Okay, good morning, everyone. Welcome. So we're in week 8, so close very quickly coming to the end of the quarter. So before we start today's lecture, are there any questions from last time or questions about course logistics? Okay, so remind me to go over project 2 at the end of class today if I forget. Okay, so after the lecture, I'll go over some uh, details of that. Um, So let's see. So today we're going to cover K-space trajectories and pulse sequences and getting to sampling, aliasing, resolution, and go over sort of what are the design requirements for designing an MRI acquisition. And so by the end of today's class, hopefully you have a sense of what goes on under the hood when the MRI technologist sits down and types in some requirements and what that software actually does. Okay. Okay, just to remind you, what we're measuring in MR is we're measuring the Fourier transform of our object. Okay, so at every point in time, we're getting a sample of the Fourier transform of our object. Okay, so the basic picture is assume this is Kx and this is Ky. Okay, and so we might start off at some point here, and then we will want to collect points along this whole plane. Okay, so as we go through the MRI sequence is essentially collecting all these points in K-space. All right. And when we've collected enough points, then we can take that data and do an inverse Fourier transform and then calculate our image. All right. So today we're going to talk about how do we collect those points. But before we do that, there was a request to go over some of the pre-lecture quiz problems because there was some let's say, diversity of answers this time. Okay. So just to remind you, if I'm at some point, let's say A minus B in K space, right? Then the pattern would look like this. Okay. So I think a lot of people picked either A minus B or minus A, B, right? And those would have the same pattern. But I think the thing you were actually looking for a pattern like that. Right. So just that's one thing to think about is if you just draw it out and put the point, then you just draw the perpendicular to that vector and you should get the right answer. And also, if this is the K space, then the magnitude of this vector is simply where you are in K space. So the magnitude of that vector is just A squared plus B squared, right? Okay. Simple Pythagorean theorem. And therefore the period is just 1 over K, right? All right. So it's nothing too complicated, but you do have to realize that you're looking for the magnitude of that K-space vector. All right. And then the other question that came about was, whether the phase was minus 90 or 90. And just remember, clockwise rotation is what we're talking about. So the spins precess clockwise. And so if I've gone a quarter of a cycle, that's going to be minus 90 as opposed to plus 90. Okay. So I think that was the major sort of diversity of answers. All right. So, but overall, I mean, these are just, these are just more to sort of get you to think about these concepts. As you see, the weighting of any one problem is very minor. Right. So any questions on those questions before we dive into the lecture material for today? Yes.
Sorry, can you explain why it was minus 90 again?
Because basically the spins precess in a clockwise rotation. Okay.
Oh,
So this way is minus 90, right? This way is plus 90 degrees. Okay. So that's just by convention. Well, that's physically what they do too. So it's not just by convention. It's we're just they just physically process that way. Okay. All right. Any other questions? Yes.
could you go over how the signal from negative A, comma B and A, comma negative B are different?
Oh yeah. So these are just different points in K space, right? So for example, this would be e to the j 2 pi ax minus by, right? So then that would mean that, and this would be e to the j 2 pi minus ax plus by. Okay. So obviously they have the same k-space magnitude, right? But the angle of orientation is different, right? E to the j 2 pi ax is going to have a positive phase as x increases, or e to the minus j 2 pi ax will have a negative phase. So it's that sort of the orientation of the spins.
But when we visualize from the image space,
Yeah.
like would that look the same?
If you took the magnitude, yes. Right. But if you could look at the phase, then it would be different. So basically, um, in general, we haven't spent too much time on that. I mean, in general, you look at magnitude images, right? And so we just look at the magnitude. And so it would appear the same from a magnitude point of view to first order. But if you take if we could look at the phase, then it would look different. And then also, if you think about adding it to another signal, then how it adds will be different as well. So everything comes down to everything just comes down to addition and subtraction and multiplication, but then you have to think about what that means. Yeah. Okay. And it's also most people, are not too comfortable with complex numbers yet, and so it is useful to think about that. Okay. Any other questions? Okay. Okay, so just to remind you, so that's a sort of a mini review of K-space, and that's what we're going to be talking about. And so we've done a lot of heavy lifting up to this point, and the whole point of that is that the gradients control where you are in K-space. Okay, and so that's the design problem we're going to be looking at today is how do we design those gradients to move us around in K-space, and how far out in K-space do we need to go? How do we sample K-space? Okay. So this was the problem that we looked at last time, where we looked at two gradients, gx and gy, and we were asked two questions: what are kx and ky at 4 milliseconds? So at this point in time, what's their value? And at this point in time, what's their value? So I'm not going to go. I'm just going to walk through, just to remind us. We'll use this as sort of a review question in terms of how I would draw the k-space according to these gx gradients. Okay, and then the homework 5, which you sort of are working on now, just has MATLAB things that are just you're doing the same thing in MATLAB. Okay. So remember, all we're doing is if I were to draw kx as a function of time, and let's say this was 1, 2, 3, 4 milliseconds. Okay. So remember, I'm just integrating that waveform, right? So you just go back to your first year calculus and you just integrate the waveform. Okay. So we know that this is going to, if I integrate a constant, I'm just going to go up, right? And then that constant becomes negative, so I need to integrate down. Okay. So that's what the waveform would look like. And then we're not going to calculate, I mean, one of those answers you can calculate and it'll give you the right answer. Okay. So I'm just going to draw what the waveforms look like. Okay. Everyone okay with that? Okay, so you know that we said last time at 4 milliseconds is obviously 0 because the net area is 0. And then here it's just whatever area this is multiplied by gamma over 2 pi. All right, so this would just be gamma over 2 pi times the area, whatever that is. All right, okay. So now let's look at the ky gradient. Okay, so same thing. 1, 2, 3, 4 times ky. Okay. So now from 0 to 1, I'm integrating a line. So what's the integral of like x? If I have a function like y equals x, what's the integral? Anyone? Come on.
X squared of 2.
X squared. Yeah, or something related to x squared over 2, right? Okay, good. So from here to here, we're gonna have something like proportional to x squared, proportional to t squared, right? Okay. How about from 1 to 2 milliseconds? What's going to happen to the area? I'm still integrating, right? Okay, so what's the integral of that thing? Anyone? Yes, you look like you want to raise your hand.
Yeah, I don't know the formula, but like it looks the same, just shifted by 180 degrees. So you're going up like that at the moment, and now you're going.
So you're going to flip it.
Yes.
Yeah. Yeah, you're going to flip it like this, right?
Exactly.
Yeah. Right, because it's accumulating area, but at a much slower rate, right? So it's going to turn over like that, right? And if you remember, if you remember from calculus, right? I mean, you have like happy face and unhappy face, right? The curvature, right? So it's the same principle, right? Okay. And then what happens from 2 to 3 milliseconds? You're starting to lose area, right? Because now the gradient is negative. So you better start going down. And how are you going to go down? Is the curvature going to be positive or negative? Any ideas? So you're going down, right? But it's the rate at which you're going down is increasing, right? Because it's becoming more negative. So it better get steeper, right? So then you know it's going to go like this, right? Okay. And then what about the last part? You're still losing area, but you're losing it at a slower rate, right? So then it's going to go like that. Okay. So luckily you guys don't have to do this for homework this year, but if you did, you'd have to review your calculus. Okay. So everything we do here, you could have done when you were a freshman, but it's just putting it all together. Okay. All right. So the thing is, you were probably better at calculus when you were a freshman than you are now. But just it's just useful to know that it is sometimes useful to remember those old skills. All right. Okay. And then this point here. So obviously this is 0. That's what we figured out last time because there's a net area of 0 there. And then this would just be, gamma over 2 pi times whatever the area is accumulated, this area accumulated there. Okay. So the nice thing is, even if you didn't know those waveforms, you could calculate those points by just calculating the area. And so one question is, what's the relationship? So, and then also you know that, for example, we talked about last time, obviously this area is twice this area, right? So you know you've moved out. The kx, this is A, and this is B, you know that A equals 2B, okay? Just by looking at the areas. All right. Okay, so any questions before we move on? All right. Yes.
So in the homework, it talks about like this thing called
The what field of view?
Yeah, so this field of view in this case, like when you say like 4 milliseconds, like what's the kx?
We'll talk about that. Yeah.
Okay.
So by the end of today's lecture, you should be able to do most of homework 5. Yeah. Yeah. Okay. So in fact, we're going to start talking about it now. So what we're going to introduce you to now is the most sort of commonly used pulse sequence in the world. Most things are based, I would say maybe 90% or more are based on some version of what's called spin warp. Okay. It's sort of the most common way of going through K-space. And this is the basic motif that we use, which is we have a GX gradient that looks like this and a GY gradient that looks like this. Okay. So let's see what happens first. So in the beginning, the GX and GY gradient are both negative in this case. So that moves us out from here to here, right? Because I'm accumulating negative area, right? And then I stop the GY gradient, so I don't move anymore in KY, right? But I start accumulating positive area on GX, and so that moves me along the line here. Okay. And so the basic idea is as I'm moving along that line, then I'm going to acquire data in K-space. Okay. So spin warp is I'm going to go line by line by line through K-space. So now let's add another thing to the spin warp pulse sequence just to give you a sense of how it works. So now what I've added is I've added the RF frequency pulse. Okay. So now we're combining the RF and the gradients together because we need both to move through K-space. So remember, what is the RF doing? It's tipping the spins. Okay. So it tips the spins and they precess, right? And as they precess, we're making them have different spatial patterns as we move through K-space. So why do we repeat this? Okay, well, one reason we repeat it is because remember, we talked a little about T2 decay, right? They're processing, but it's also decaying away. So depending on where we are, on average, maybe we only have 50 milliseconds to acquire the data. All right. So we acquire as much data as we can. So for example, the first time we go through, we acquire along this we acquire data along this part of K-space, okay? And maybe this takes us 10 or 20 milliseconds to acquire the data. And then we say, well, okay, now we need to wait and refresh the data. So we wait some amount of time, which we'll get into this in a later lecture, but for now, I'll just tell you, we call this TR, or repetition time. So we wait for the magnetization to longitudinally recover. The magnetization regrows, and then we tip it again. We have some fresh magnetization to deal with. And now you can sort of see the GX gradient is the same. And just to give us name, this is called the readout gradient. Okay, and this is called the phase encode gradient. And now you can sort of see the readout gradient is the same across repetitions, but this gradient here has half the area, right? So I'm only going to go out. I'm not going to go out as far in the KY direction. So now my starting point is different. Okay, so now when I zoom across KY, I'm collecting a different line in K space. Okay. And then for the last repetition here that I'm showing you, there's no GY gradient. So I just stay on the the KY equals 0 axis. I just go out this way, and then I come along and I zoom across here. Yes, question. Sorry, can you say that again? Yes, yes. Remember, this is coming from the radio frequency coil, and these gradients are due to the gradient coils. So now we're starting to combine two things together. Okay. So that's a great question. And let's see, I was going to say one more thing. Oh, yeah. So these are basically these two gradients. You can call these are like the dephasers. Okay. So those are the initial ones that sort of get you out to some initial point in K space. So in the homeworks, when we talk about the dephasing gradients, those are what we talk about. Yep.
The RF, the first signal makes the spin tilt, right? So
it flips the spin. Yeah.
What do the other two like graphically?
Okay. So imagine I tip the spins, and remember the signal decays away. Right. So then I need to wait for the signal to recover, and then I tip it again and I get a shot at it. So it's like you're sort of like it's like each time you're licking the ice cream. Like you have an ice cream, you lick it, you go, yum, 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 yum. Okay. And then you're at some point, like you wait for your taste buds to recover, and then you can lick it again. Okay. Or the same thing is I'll get you doing a question. The same thing is like I think everyone is familiar with like a toilet, right? Like if you flush it, right, and it's full flush, if you try to flush it again, nothing's going to happen. So you flush it, and you got to wait for like 30 seconds for it to fill up, and then you can flush it again. So that's the same thing.
Yeah, I understand you need some time for it to recover, right?
Yes.
Limited time for it to come back to the original position.
Yes.
My question is, I don't understand graphically, as you show us show us before with the pen.
Yeah.
What the GX and GY are doing to the.
Oh, so the GX and GY, so every spin is just processing, right? But every spin processes differently depending on the GX, GY. So that's where you have to think about all the spins. That's where we talk about all the phasor patterns. So like say I have these two, I can only do two, right, with my fingers. So let's say I flip them. So they flip, and then they start spinning differently, depending on where I are. Initially, they spin the same because I'm at the center of K space. But as I apply these gradients, they start spinning differently. And I have to think about all the spins all over all the space, acquiring different spatial patterns. Yeah. There was a question there?
Yes, just for understanding, the GX was the readout and
Yes.
the GY was the phase encode.
That's the name.
So what are the dephasers? Both of them? Or
Yeah, the dephasers are both of them. They're basically, you can think of them for now as they're basically just taking you out to some initial point in K space.
So it's always these negative in the beginning.
They could be positive or negative, but the idea is you're not really looking at the data during that time. It's almost like those are taking you to some starting point, and then it's during the readout part. So this is the readout, yeah. So if you want to be more specific, you'd call this like the phase encode dephaser, the readout dephaser, and then this is the readout gradient here, because that's when you're reading it out. Okay, question.
It seems like it's moving in like a kind of zigzag pattern, like across like the loops up. So is that like is that like trying to apply the gradient across like the entire case space or like what's?
The idea is, the basic idea is you just want to zoom out here and then collect data.
Okay.
You want to zoom out here and collect data. So you want to actually like, it's like you want to run as fast as you can to the starting point and then you collect the data and you run to another starting point and collect the data. Okay. Yeah. Question?
Data collection, dephasing, always two different things, or could you collect data as you're dephasing?
You can, but it's more complicated. So if you want to do that for your project, that'd be really cool because that would be like you basically have to like the nice thing about collecting here is life is simple, right? Things just go bup, 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 bup. If you want to acquire here, then you have to people do that. It's something one term for it is actually it's called ramp sampling. Right, so you're zooming through case space in some weird way and you're collecting data as it goes. So yeah, that's also possible. And that would be like considered more advanced reconstruction. Yeah. Question back there.
Like a big question, but like with the readout pulse, like that's just in the X direction. Do you say like you're scanning like through an object or whatever, or?
Yeah, so that's a good question. So there are basically an object has like a physical X, Y, Z, right?
Yeah.
But when we hear this is what we call logical. Basically, X gradient is always the readout. So basically, I could have this is my physical X, but I say I actually want to acquire data this way through my object. So this would be the logical X. And so the software just does all these rotations for you. Yeah. So as a software designer, as the MRI designer, you don't have to think about that. Someone has written the software that just translates things for you. And we'll show some examples of what the interface looks like. Okay. Yes, question.
Why we have a Z gradient? How does the readout in phase, like what is the Z direction?
Oh, so yeah, I could easily just add like I could actually add like another like a GZ gradient if I wanted to. Like a GZ dephaser. Yeah, that could be like yes, for first order, yes. You know, obviously there's much more complicated, but yeah, for first order, the GX is always going to be the readout. The X gradient is always the readout by convention, and the Y and Z will be your phasing codes. So that would just take you out to some place in three-dimensional case space. Yeah. So you can imagine doing that, and it would just take forever, right? But people do that, and we'll get into that. Right. Okay, that's great. So then if we added some additional phasing code dephasers, then we could acquire more lines. Okay. And so that's the basic idea behind an MRI pulse sequence. We're just going through case space. Okay. So let's do some examples of that. So for example, let's say my object was a rect function like this. Then we know the Fourier transform is just a sinc, two-dimensional sinc function. Okay. So the idea is if we did a similar pulse sequence, we'd just be going through case space line by line by line by line and collecting the data. Okay, so that's essentially what we expect to see. So in this example, I have my object here. Every time I go through case space, I'm going to show you a line through case space, and every time I get one of those lines, I'm going to just store it in this array. Okay, so let's see what this looks like. Okay, so you can sort of see the signal is fairly small, right, until I get close to the center of the sink. And then you see the signal up, and this corresponds to this part. Okay, so I'll play it one more time. So this is sort of what it would look like if you're acquiring MRI data. Okay, so this is the signal that'd be coming into your receiver, and as it comes in, you just store it in this array, and then at the end, you do the inverse transform and get back to your object. Question?
So, since the pattern is so uniform, I feel like we would expect it just to have one peak.
Yeah, so remember this is a rect function, right? And a rect goes to a sinc. Yeah, so basically anytime you have sharp edges, you need lots of frequencies to represent a sharp edge. Yeah. Okay. So obviously if I made this rect function really, really big to go to infinity, then it would just be one frequency, right? It'd go to a delta function. But as I make it smaller and smaller, like in the limit, if I make it a delta function, then the transform is going to go to 1, right? So it has all frequencies. Yeah. So that's version of what's called the uncertainty principle that also is in physics and other domains. Okay. All right. Okay, so that's just one way. And so what we've talked about is so basically think of this as K-space. I'm trying to fill up K-space. Like I have all these pigeons and I just want to fill up these boxes with pigeons. Okay. So what we've talked about is what's called Cartesian spin warp. Boom, 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 boom. Okay. So that's one way of filling up K-space, line by line by line. And by far, that's still the most common way of doing that. All right. But I can imagine going through K-space like this. And in fact, you'll do this on homework 5. That's one way of going through K-space. So that's like a square spiral. Okay. Or I could do radial. What does this remind you of? What other modality have we done in this class that has a radial through K-space? CT, right? So you can make MRI look like CT. Okay. So in fact, people are trying to make, for example, certain acquisitions, MRI can do just as well as CT for like bones and things. And then this one is zigzag. It's also called EPI, which you'll also have a chance to do on your homework. All right. So just as a word of caution, we're going to go over the design for this one. We're going to look at the design rules, but the principles are always the same. But if you just copy what we do for this and apply it to these, you won't get the right answer. Okay. So you have to go back to sort of the design problems and think about what it means for each trajectory. All right. Okay. So in fact, this is the single shot planar imaging, which you'll have opportunity to do in your class and in your homework. And so here's an RF pulse. So this is an example where we just do one RF pulse, and then we just want to go through K-space very quickly. Okay, so this is what we use. We'll see we use this for functional MRI because we don't want to wait to acquire data while the brain's doing all this stuff. We want to be able to just acquire all the data very quickly. And as you can sort of see now, the frequency, oh yeah, the readout is also called frequency. Okay. So readout and frequency is the same meaning. It's just there's different terminology. Phase is still phase or phase encode. Okay. And so you can sort of see here now, this is just like this gradient looks very different than what we just did. And this gradient looks very different. And so you have an opportunity to sort of look at these gradients in your homework. All right. Okay, and then this one, let me think. I think I have to share my computer sound on this. Let's see, share computer sound mono. All right, so let's see if this works. So this is, the other cool thing about gradients is that we're switching them very quickly. And for example, that EPI waveform, the gradients, as you can sort of see, go up and down, and they tend to be around audio frequencies. And so therefore you can actually make nice sounds with them. Let's see. I'll get the sound better on this.
A continuing problem with fMRI is synchronization of the stimulus with the scans. The Imaging Research Center has addressed this problem by requiring the gradients themselves to issue audio prompts to the subjects.
Sound files can be directly recorded into the SGI. A C program is written to store the file in an array. It is then downloaded in real time into the gradient waveform memory using the pulse program shown here. Only a few lines of pulse program code are necessary to output the array to the gradient waveform controller. Shown here on the oscilloscope is an example of the current output of the gradient amplifier of the digitized bagpipe sound file. Here is a view of the Brooker Paravision pulse programming tool showing the 32 kilobyte digitized waveform of the Scottish bagpipes played out on the slice selection gradient.
So basically they're using, like that's like a $3 million audio speaker, right? So basically they're playing the waveform into the gradients, and the gradients are causing time varying magnetic fields, which cause currents, which cause vibrations because they're within the large B0 field. So you have currents within another field, and then if you go, remember Lenz's law, right? Or, Faraday, all the whatever, the force equals Q cross V, right? So that's going to cause that force onto the wires. So that's what's the.
Swallow. Swallow. Swallow.
Okay, so what you're hearing there is you're hearing the gradients are telling the subject to swallow, but then the next thing you hear is like, that's the EPI pulse sequence. That's that going back and forth, zigzagging through K-space, okay? So for those of you who end up doing MRI, one of the interesting things is the more you're in the MRI scanner, the more you sort of can hear what pulse sequence they're playing. So like if I go into MRI scanner, like if I'm having an exam done on me, let's say in the clinic, then a fun thing to do is I try to guess what they're doing, right? I'm like, okay, I think it's that pulse sequence, or I think it's this pulse sequence. Because basically the gradients tell you what they're doing, all right? So anyways, there's a copy of this movie on Canvas, so you can download it and watch it as much as you want. But we're going to move on.
One question.
Yes.
What's the real time it takes to go through full K-space? Because like when you're in an MRI system, sometimes it takes like 15 or 20 minutes. Why is it that long?
We're going to get to that.
Okay.
And your job, if you so decide, is to go come up with better methods so people don't have to wait so long. So that's what MRI people are always trying to do, is try to go, how do you go faster? So we're going to spend the next few lectures just talking about that. So we're going to start off with the very basics, and then we're going to get you as much as we can to like state of the art, like deep learning, and talk about how that can allow things to go faster. Okay, so it's a lot to cover, and you're not going to, we can just give you sort of the highlights of it just to show you that this is where the field is at. But the interesting thing is it's you're going to learn basically the basic concepts will at least allow you to understand what's going on right now in MRI technology. Okay. All right. So this is the basics now. K-space sampling. All right. So this is where we're going to introduce these ideas of FOV stands for field of view. Okay. So there's going to be field of view. We're going to do two-dimensional imaging. So there's field of view in the X direction, field of view in the Y direction. Okay. So that's basically just saying, like if I have a head, I need a certain field of view. My object has a certain size, so I want to declare a field of view. If I was going to scan like an orange, then I could make the field of view smaller. I just say, hey, my object's not as big, so my field of view is smaller. So that's going to have some impact on the design requirements. And then the other thing I want to specify is delta X, delta Y. This is my resolution. Okay, like how many, what's the size of every pixel in my image? Maybe it's 2 millimeters, maybe it's 3 millimeters, okay? So obviously if it's like 10 millimeters, then that's very coarse resolution, right? And then if it was 1 millimeter, that'd be finer resolution, all right? So it's the same thing like when you buy a TV, right? It's like, what's the resolution of or your screen, right? Okay, so that's what you specify. So there's 4 parameters that you specify, at least for now, for these basic parameters. And then our job is to come up with the design rules that come up with 4 things in K-space. What's the spacing, delta Kx and delta Ky of my samples in K-space? And also, what's my width, Wkx and Wky? How far out do I go in K-space? Okay. So you can think about it this way. It takes time to measure each point in K-space, right? So the bigger I make the width, the farther I have to go out, it's going to take more time, all right? Also, the smaller I make delta K, then I have to finally sample it. So that's also going to take time, all right? So what we want to do is we want to make delta K as big as we can, right, to save time. And we want to make these as small as we can, right? So we want to figure out what are those limits? How can we go? And so what we're going to do is we're going to come up with sort of the basic design rules. And then when we talk about advanced imaging, we're going to show how to break those rules. Okay, because if you're stuck with these rules, there's a certain amount of time it takes. So the only way to go faster is you got to break the speed limit. Okay, so we're going to talk about that. Okay, so sampling K-space, just to remind you, you've looked at this already in one of your MATLAB grader problems, but this is my object, this is the K-space. And let's say I just threw out every line, vertical line in K-space, then you saw you get something weird like this. So we're going to find that this is a form of aliasing. Okay. So one of the design rules that we obviously need to come up with is we don't want this to be the image, right? Nobody wants to have this, like, if this is the image that your doctor gives back to you, you're not going to be happy, especially if they're planning on doing surgery of your head. Okay. Similarly, you would not be happy with any of these images, right? Okay. So here I've thrown out every other line in K-space. Here I've thrown out every other vertical and every other horizontal line in K-space. So what we're seeing is that the answer we expect to get is that if we throw out samples in K-space, if we don't sample finely enough in K-space, the downside is we're going to get image replicas. The image is going to overlap on itself. Right. So let's think about one sort of way of thinking about aliasing sort of intuitively. So these are sort of remember, I have spins in different locations. Originally, they're all aligned at the same phase. And if I apply gradients and weight, then they all sort of advance in phase. Okay. And so notice that these spins were going faster, these were going slower. But notice what happens if I look at these. This is in this location and this is in this location. But if I look at the spin phase evolution, it looks exactly the same. Okay. So remember, I don't get to see what any one spin is doing, right? I just get to see all the sum of the spins from the coil. So if all I can see is, so since I can't really see it, the contribution of this spin and of this spin would be exactly the same. So this means that when I did my inverse Fourier transform, this would be overlapped with this spin. Those two spins appear as if they're coming from exactly the same location because I can't tell. Okay. Similarly, these two spins are doing exactly the same thing, right? And so the way they would enter into my overall sum, they would actually have the same contribution. So that's where that overlap is coming from. And so what's the solution? Well, here I've done a 180-degree jump from here to here. I've done a 135-degree jump from here to here. So I need to take smaller jumps between these, right? So if I do that, then now look at this phase of evolution here. It's different from this one. Okay. So the idea is I have to sample more finely in K-space. I have to not just sort of say I can go from here to here. I have to sort of go a little more slowly in K-space so I can figure out the spin evolution to capture the different locations of my spins. All right. Okay, I think I'm going to skip this one. So let's just move ahead to the process of sampling. Professor McVeigh covered this a little bit, so we'll just review it rather quickly. So remember that we have these continuous signals, right? We want to sample them. So I want to go from g of x to some g bracket of n, and these are my samples, okay? And same thing with MRI. I can't afford to, I need to sample K-space, right? It's not like I can get infinitely resolution in K-space. I'm going to sample it, okay? So I need my comb function, which looks like this, and this is the comb function with spaces 0, 1, 2, 3. I'm just sampling at a very integer value. And then I want scaled comb functions that have a spacing of delta x. And don't worry about all these sort of leading factors. That's more mathematically correct. But the main thing is I just want something that samples every delta x. And the most important thing is that the Fourier transform of a comb is just a comb. All right. And so if I have a comb with spacing of delta x in one domain, then by the scalar theorem, it's got to have a spacing of 1 over delta x in the other domain. All right, so that's the main thing to remember, and that's represented here. So all you really need to remember is if I'm finely spaced in one domain, I'm going to be widely spaced in the other domain, and conversely, if I'm widely spaced in the other domain, I'm going to be narrowly spaced in the other domain. So it's like this. This is another form of the we're seeing the uncertainty principle again. Okay, if you squeeze here, you expand there. If you expand in one domain, you squeeze in the other domain. So if I make delta x really big, 1 over delta x gets really small. If I make delta x really small, 1 over delta x gets really big. That's all you need to really keep in mind. So what's a little different about, so in MRI, what we do is we sample in Fourier space. Okay, so let's look at an example of this. So here's my rect function here. And remember the Fourier transform of that's just a sinc function. Okay. And let's say this is, say, whoops. So this is, the kx direction. So what we do now is we sample this sinc function. So we're getting samples in k-space. And then we take the inverse transform of that. And the question is, what's the inverse transform of those samples? Right? So that's the first question we want to answer. Because if we know that, then we know, what design requirements we need to satisfy to figure out how finally do I need to sample the sinc function. Right? So the Fourier sampling is just delta kx, right? So I'm going to have that sampling delta kx. And by what we just talked about, if I'm spaced delta kx here, I'm going to space 1 over delta kx in the other domain. Right? So that's the first thing to remember. The other thing to remember is this is the waveform. This is like the ideal sinc waveform. Sampling is I multiply that waveform by this comb function to give me my samples. Okay? But from the convolution theorem, that's the same as taking my object. The multiplication becomes convolution, convolving my object with the inverse transform of the comb function, which has spacing of 1 over delta x. And remember, anytime you convolve something with a direct delta function, it just moves the object to that location. So this is just going to take my object and replicate it with a spacing of 1 over delta kx. So these are now going to be spaced 1 over delta kx apart. And that's the aliasing part. So now you can sort of see where we're going. If that sampling is going to replicate my object, I better make it so that when they replicate, they don't overlap. So that's going to be the design rule. All right. So that's where we come up with what's called the Nyquist condition for MRI. Nyquist applies to lots of things, but for MRI, this is specifically what we mean. We have some field of view. Field of view is just telling the scanner, my object's about this size. I need to have a budget for my object. And so if a head, typically I need about 20 centimeters, okay, for most heads, okay, for most human heads, all right. So if I'm going to replicate that field of view, then I'd like it so that that spacing 1 over delta kx is bigger than that field of view, right? So the requirement is simply that this 1 over delta kx is greater than the field of view, or equivalently, delta kx is less than 1 over the field of view. Okay, so let's look at this. So this means that as I make the field of view bigger, right, the bigger the object I want to scan, this delta kx gets smaller, right? That number becomes smaller. If I have to sample more finely in k space, that's going to take me more time, right? Because I only move a little bit each time. So therefore, there is a cost to scanning bigger objects. Okay, so you never want to set the FOV. If I'm scanning like a lemon or a lime, I don't want to set the field of view like this, right? Because that's going to make my delta K very small, right? I want to make the field of view just right, so I'm not sampling too much, okay? I'm not setting the delta K too small. And if I don't set it, when this 1 over delta Kx is less than the field of view, then the objects overlap. Okay, so I typically want to avoid that, all right, for basic imaging. Now, a couple of lectures from now, we're going to show how we can allow things to alias and we undo the aliasing with special tricks. But for now, for your homework, this is the design rule you want to go after, all right? So here's an extreme case of aliasing. If, let's say, this is my sinc waveform, and made my delta kx equal to 1, right? So then my samples, I just get a 1 and 0 everywhere else. All right, so if I take the inverse transform of that, I'm taking a delta function, inverse transform, that just leads to 1. Okay, and as you can see, what that means is I've made my replica such that all these rect functions line up next to each other so that their sum is just 1. Okay, so obviously this is not a good sampling of my function. Okay. We can also do 2D comb functions, and so just which is useful for MR. So same thing, we can have spacing delta x, delta y, and then in k space, the spacing is just delta kx, delta ky. And so now what we end up with is these spacings are now 1 over delta K, or sorry, this spacing here is, I've got delta K spacing here, okay? So this is now, if this is my object, this is a 2D sinc function, right? This is the Fourier transform I want to sample. So the way I represent it mathematically is I multiply it by this 2D comb function that has samples at delta K. And so this is what my samples would look like. And this is what I actually would store into the computer. This is all I have for the computer, these samples, okay? So I want to say, well, what, if I take the inverse transform of all these samples, what am I going to get, right? So we go back to Fourier theory and we say, okay, well, I have my object. I multiplied in the Fourier domain, so therefore I must convolve in the image domain. I take the inverse transform of this comb function. This is a spacing of delta K. So therefore, this has a spacing of 1 over delta K. This convolve with this just takes my object and plops it at every delta function. And so now these replicas are spaced at 1 over delta K. Okay. So that's all you need to know about sampling. So the sampling in MRI gives you image replication. Okay. And your job is just to make sure that the images don't overlap. Okay. So once you know what the field of view is, then you know what the delta K is. Okay. So there's going to be 2 design rules, 1 for each axis. Okay. So typically you're going to be given a field of view of Y and a field of view of X. The design requirement is that 1 over delta Ky is greater than that. But for all your homeworks, and typically what's done in practice is we just make it so it's equality. So for example, if I give you a field of view of Y, you could just say, well, delta Ky, I'm just going to set it equal to 1 over a field of view Y. Okay. And delta Kx, similarly, I'm just going to set it equal to 1 over a field of view X. Okay. So so in your MATLAB code, you're just going to have lines that look like that. You're literally going to just calculate that. Okay. So the nice thing is after all this heavy lifting and, all this sort of theory, the design rules turn out to be super simple. Field of view, take 1 over it. That's your delta K. All right. So any questions on that? Okay. So let's do an in-class exercise. So here's my object. It's a cosine 2 pi 3x plus 2y times rect x over 3, rect y over 4. And you are supposed to figure out what's the delta kx and delta ky to avoid aliasing. And you can assume spatial units of centimeters. Feel free to talk to your neighbors, open up the online poll, and we'll regroup in a few minutes. Okay. Okay, another minute. Sort of think about this, and then we'll regroup. Okay, let's check in class. So we have an online poll. So at the count of three, just say really loudly what you think the right answer is. 1, 2, 3. Good. Okay, and C was also the most popular answer online. So let's just go through this together. So what is the field of view in the x direction? Anyone? Of this object? 3, yeah, because it's rect x over 3, right? So rect x over anything has a width of that. Rect x over w has a width of w. So that would be the field of view. And similarly, field of view of y is equal to what? 4, right? Okay. And then therefore applying the design rules gives you 1/3 and 1/4. Okay. So you can sort of see we're not talking about like higher level math here. It's pretty straightforward. All right. Okay. Okay. So the next thing we need to talk about is windowing. Windowing is saying, so we've talked about the sampling. What's the delta K? Now we need to talk about how far out do I go in K space. Okay. So that's going to determine my width, my window. So windowing looks like this. This is the K space I have. And for example, like a rec function that goes out to plus or minus infinity, right? So I don't really want to go out to plus or minus infinity because that's going to take forever, right? So I need to say, I'm only going to look at the data within some K space window. So I need to multiply my K space by some windowing function. That's a function of Kx and Ky. And I'm going to end up with a windowed function G sub W Kx Ky, right? So in this case, I've also multiplied by a function K space. So therefore, when I look at the inverse transform, I need to convolve with the inverse transform of that window. So what that means is I'm going to be taking my object and convolving it with this windowing inverse transform. All right. So this is going to give me a modified version of my ideal object. So we want to talk about what is the requirement, what are the requirements on this windowing function? Okay. So let's first of all take a look at what that effect has, just sort of intuitively. So this is my object here. Okay, so it's a two-dimensional rect function, and its inverse transform is a two-dimensional sinc function. Okay, and I'm saying, well, I don't really have time to acquire all of these samples. I'd only want to acquire samples in some limited space of K. So I multiply my Fourier transform by this windowing function here. Okay, I don't know why I called it M, but anyways. And so this gives me my windowed function, which just has samples here. So I'm assuming I'm not acquiring any of these samples out here. Okay, just only within this window. So this is a multiplication, right? So this is a multiplication equals that. Okay. So therefore, in the Fourier transform, I have to convolve, right? So I have to convolve this with the inverse transform of this, which is just going to be a sinc function. Okay. And you notice the sinc function is wider than this sinc function, right? Because this has a big rect function going to this sinc function. This is a smaller, a narrower rect function, so it's going to give me a fatter sinc function. So I imagine convolving this with this is related to sort of your first MATLAB homework where you convolve the cross with Gaussians, right? So essentially you saw that blurred it. So now every place I have a voxel, I can imagine putting this sinc function there. And so every voxel is going to be blurred out into a sinc function. And so when I do that, you see I end up with a blurred version of my image. All right. Which also makes sense because remember, if we say we're losing the higher points in K space, so we're losing detail. So we expect to see a blurred version of my original image. Okay. Okay, so let's go through the math. So in this course, we'll use rect functions, very simple windowing functions. So rect of kx over wkx, rect of ky over wky. So this just tells me the width of my function wkx, wky. Okay, that's the size of my window. The inverse transform of that is just this. So sinc function here, wkxx, and a sinc function wkyy. And so if I want to know the effect on my image, I just take my object and I convolve it with these sinc functions, right? Okay, so let's talk about the effective width. So when we talk about resolution, we know that, okay, I'm convolving it with something. And so one way of talking about resolution is like how wide or how sort of what's the width of the function I'm convolving it with, right? If I have a very large sinc function and I convolve it with my object, I expect that to do a lot of blurring, right? And if I have a very narrow sinc function and I convolve it with my object, the blurring won't be as much, right? So in essence, we want to see the effective width. And so you've already seen this when we did the RF pulses, but the area under a sinc is just the Fourier transform value at 0, right? And so it turns out that the width of this sinc function, which is just the function that has the same area under the curve, is just going to be this red curve, okay? And it turns out that effective width, luckily, has a very simple answer. It's just 1 over WKX, okay? So we can say, if I want to go out 1 over W, if I have a width of WKX in Fourier space, that is going to correspond to a blurring function that has a width of 1 over WKX. So once again, we have a very simple design rule, all right? So one way to think about that is, let's say I had a, let's say I had an object that was changing 1 over WKX. So this is an object that has a certain frequency, right? So if I want to image this object, if I want to have any chance of sort of being able to figure out what the object is, I better have something in my Fourier transform that can multiply that and sort of looks like that object, right? So here's a function that looks like my object, right? So therefore, I should be able to capture this frequency component in my object. So this has a period of WKX over 2, okay? So that just means that if I want to capture that object in K space, I need to have a point that has a frequency of WKX over 2. And so my full width is WKX. Okay, so that's another way of looking at it. And this is just an example of what happens when we get to the limit. So here, the window is, so these are spaced. So the spacing here is, the spacing is 1, right? Right, and I said my effective width is 1 over delta kx, right? So here my width is equal to 1. Here it's equal to 1 over 1.5. Here it's equal to 1 over 2. Okay. So if I convolve my object, which is just 2 delta functions, with the sinc function, then one sinc function is here in blue, one's in green. And if I sum the two up, I just get one overall function in red. So at that point, those 2 dots, I can't really resolve them, right? So when I'm right at the limit of my design function, I can't resolve those dots. The effective width of my sinc function is just too big, okay? But now if I go to WKX 1.5, I've gone out farther in K space, so therefore that width is now 1 over 1.5. If I do the same experiment, here's my green function. Here's my blue that's convolved the sinc with one of the delta functions. The green is with the other delta function. And now if I look at the sum, then you can sort of see that if I had sufficient SNR, I would be able to tell that there's 2 dots there. Okay, so this is sort of getting at resolution, right? If I have 2 dots, can I tell them apart? All right, so it's showing the farther I go out in K space, that means if 2 dots are spaced closely together, I'll be able to see them better. And if I go out even farther in K space, now I'm convolving each of those delta functions with a narrower sinc. So you can sort of see here, each of these sincs is narrower. And so when I look at the sum, I can very easily resolve these 2 dots. Okay, so this is just telling you why the width of the sinc function is related to resolution, which is your ability to resolve objects that are close together. All right. So if we put it all together in MRI, we've got sampling and windowing. Okay. So let's go through this. So I have my object. Here's its Fourier transform. Remember, I sample those Fourier transforms so that I convolve with these space Dirac delta functions. I also window it, so I'm going to be convolving with these sinc functions. What I collect in K space is just samples within some window. And therefore, when I inverse transform it, I'm going to get these replicas where each one of these replicas is a blurred version of my original image. All right. So that's just explaining what that is in math. And so now here's the design rule. So yes.
Or like, is it possible to make do the sampling and windowing part in a time resolved way? I don't know if that's the correct terminology, but if you could use an echelon or something to in microscopy to um move the pulses in time so that they're each moving a different time, each of the window or each of those flips. I don't know.
Well, strictly speaking, at every point in time, you're at some point in K space, right? Because that, well, I mean, yes and no. I mean, you could come up with, I suppose it's something to think about. I mean, I suppose there are ways. I mean, you can certainly come up with um, phase distributions that are not a Fourier component, right? And also, and actually, we'll find that in practice, we don't actually have these Fourier components because things aren't ideal. And so in that sense, you could be sort of simultaneously sampling different Fourier components at the same time. So yeah, I mean, that's something to think about. I'm not sure that's getting to your question. Yeah, I guess what I would say is uh, almost anything is possible. So if you want to try it out, that'd be an interesting experiment. So you could look at nonlinear gradients, something called O space, they're like K space, and there's different things. So we're just doing the most basic one, but yeah, there's variations that you could think about. Okay. Okay, so this is really the final sort of, what I've gone through is sort of just to motivate these design rules, but literally all you need to do in your homework is just apply these very simple design rules. So remember, you're going to be given field of view of X, field of view of Y, and you're going to be delta X and delta Y. Those are typically the four parameters you're given. So you simply say delta X equals 1 over field of view of X, delta KY equals 1 over field of view of Y, and then WKX is just 1 over delta X, and WKY equals 1 over delta Y. Okay, so that's all you really need to do. And then you just need to design the gradients to achieve those design rules. And so we'll go over an example of that for spin warp. All right, so the first step is take the parameters, figure out delta KX and the width, and then convert those into what your gradients have to do to achieve that. The sampling and also the width of K space you cover. Okay, so let's do this simple one just to make sure everyone's on the same page. So now we have another object. Well, no, actually we have the same object. So go ahead and sort of think about what would be a reasonable choice for the resolution of this object, and what are the kx max and ky max parameters you need to achieve this resolution, okay, given this object. Okay, about another minute. Okay. So for those of you in class, just at the count of three, just say really loudly what you think the right answer is. 1, 2, 3. C. Okay. So let's see if it's C or not. Okay. So let's look at this object. So first question is, we've seen this object before. Do I need to worry about this guy, these parameters at all? Because those are determining my field of view, right? Okay. So remember, field of view has no effect on my resolution, right? Okay. So I can ignore that part of the problem. Okay. Everyone okay with that? Right. That's just telling me how big my object is. So that determines my delta K, but it's not going to affect how far out I go in K space. Right. So now I need to think about what's resolution I would need for this object. All right. So therefore, it's going to be what's the frequencies in this part of the object. Okay. So if we think about, let's just look at the cosine 2 pi part. So let's say I just look at cosine 2 pi 3x, right? So that has a kx of 3, right? So if I just want to guess, I might guess, well, probably I need some Fourier component of at least 3. Okay, so that's one way of looking at it. And then similarly, the other part there's a cosine, 2 pi 2y, so that way ky equals 2. So if I just had to guess, I might guess it might be B, right? Because I need, to go at least to 3 and 2 to be able to capture these components. Okay, but let's take another look at how we would think about it from a resolution point of view, which is if I have this function here, so this period 1 over kx is equal to 1 over 30. Okay, so I have basically, if I think of the cosine, right, the period is 1 over 3. Okay, and this means that, going from something here, something positive, sort of like, let's say this is positive, right, and then something negative, right? I can think of my resolution probably would make sense to have those be my resolution cells, right? To go from something positive to negative. So my resolution should probably be delta x equals 1 over 6. Okay, so that'll be a reasonable resolution to have for an object that's oscillating with that period, right? So therefore, I know my WKX is just 1 over delta x would equal 6. Okay, just applying the design rule, right? And remember that WKX is the whole span, right? But I only have to go out, there's a KX max and say, let's say a minus KX max, right? So my KX max, assuming symmetry, would just be WKX over 2 equals 3. Okay, and this matches sort of also the intuition I would have by just knowing that that's the highest component I have. All right. So remember, how far you sample in K space is determined by sort of what sort of frequencies you want to sample. How finely you sample in K space is determined by the size of the object. All right. Okay, and so then a couple slides just to show you how this gets translated into real life. So this is actually a screenshot from a GE console. So if you had a GE MRI system, you'd get very familiar with things like this. And so let's take a look at some of these parameters. So first of all, you'll see things like flip angle, right, that we've talked about before. So here's a flip angle of 60. We'll talk about echo time later. Here you're seeing field of view, 24. This is saying I want to do a 24 centimeter field of view. And they're not giving you resolution here, but they're giving you 256 by 128 frequency and phase. Okay, and they're also saying the phase field of view is 1. So the way I would translate these parameters, is I know the field of view of x is 24. Okay, And the resolution in this case is just the field of view of X divided by the matrix size. So here frequency is also, remember, frequency or readout is the X direction. So this is divided by 256. So that's how that would get translated. All right. And then behind the scenes, the software is just calculating the delta K and the width based on these parameters. Right. Now, field of view of Y, in this case, the way they specified it is just 1 is like a factor that you multiply the field of view of X by. So 1 times 24 just gives me 24. And delta Y in this case is 24 over, what is it? 128? Okay. So that's just how that manufacturer decided to implement it. So basically, because people think about, okay, I want a field of view and I want this many voxels this way and this many voxels that way. And so you can think about voxel size, or you can think about how many voxels you want per axis. All right. And now this is a Siemens console. And you can sort of see here that you're seeing here an example of what's called graphical prescription, where they're basically trying to say, I want to acquire some data and I want to acquire in this slices. And you can sort of see it's not quite aligned with it, like it's sort of tilted off. Okay. So essentially, this is where you sort of have, even though X, Y, Z are like this, the software is smart enough to know if I want to acquire something like this, I still call this the X direction and the Y direction. And the software just does the graphical rotation for you. And let's look and see what they've specified here. So they've got a field of view of 220 in millimeters now in the redirection and 100% field of view. So the way I'd interpret that is I'd say field of view of X equals 220. Okay. Field of view of Y also equals 220 because it's 100% field of view phase. And now I look around, I'm like, well, I have no idea what the resolution is. Right? There's nothing on this page that tells me what the resolution is. And that's because Siemens, you have to go to another tab called resolution. Okay. So every manufacturer is going to have a different way of doing it. All right. And so once you get used to it, you just know, okay, I got to look here, I got to look there. So if I went to resolution, I would expect it to either, and I don't remember what Siemens does, but it would either be the size of the voxel or it would also be what's called the matrix size. All right. Yes, question. Yeah, in this case, the field of view phase, you see it's percent, right? It's just sort of how large is the field of view phase with respect to the field of view read. So basically, I'm given the field of view, this is the field of view X, right? So I know that's 220. And the field of view Y is just 100% of that. So it's the same in this case.
Does this relate back to the curves we saw in the beginning of this?
Yeah, so remember read is always going to be GX, and phase for this class is the GY. Okay, that's just the convention. And so anytime you read an MRI paper or something, that's just the thing. And also, just to keep things confusing enough, this is also equals frequency. All right, that's just by convention. So that's just, we have to introduce that notation. So when you read things, so for example, when you do your projects, and you'll see that, okay, this is readout, this is phase. And so that's basically logical X, logical Y. And then if you do 3D, then there would be Z as well. All right. So those are good questions. Any other thing before we, okay. So let me see where we're at. Okay, so we're going to sort of just start on how we actually apply this to an actual pulse sequence, and then we're going to finish that up next time. So remember, you're given these, or somehow you derive these input parameters, right? In the homeworks, I think you're just given these, right? And you need to figure out what these are first. And then the next thing we're going to talk about is how do we now translate that into the gradient design. So we're going to revisit the similar pulse sequence. And here, once again, we have the RF pulses. We have the readout or frequency gradient, and we have the phase encode gradient, right? And remember, these are just taking us line by line by line by line through K-space. Okay. So we're going to come up with the gradient design for this very simple case. And then for your homework assignments, you sort of need to go back to this and sort of do a similar exercise, but don't, if you copy and paste what we do for spin warp, it's not going to be what you need for your homework assignment, but the amount of calculation is the same order. It's literally 1 or 2 lines at most for each gradient, okay? Okay, so let's talk a little bit about what this looks like. So remember, we have our RF and we play it out. We have for spin warp, this looks the same every time we go through. And the phase encodes, we just change the size of the gradient. And so if I look at KX, that's just doing the same thing every time, right? So it's just taking me to some negative point in K space and then zooming across K space, okay? And then if I have a KY gradient, it's just taking out me some negative part in K space, and then I hold that part in K space, right? I don't move because I've turned off this gradient. And then the starting point just varies with each phase encode, okay? So at every rep, I'm encoding a different KY line, all right? But I'm always doing all of KX for spin warp. So let's talk a little bit about how the sampling is done in KX, okay? The sampling is done in KX simply by, as the signal is coming in, you're just digitizing it and storing it. So it's basically just done for you. So that's the sampling in KX is just intrinsically done that way. And you can sort of see here, this cosine omega naught t, sine omega naught t, what is that doing? Okay, remember we had this e to the minus j omega naught t term, this precession, right? So our signal coming in has this on it, right? And we're saying, well, that's sort of a pain. I don't want to have to deal with that. So this is electronically, we're just multiplying by e to the j omega naught t. Okay, so we're canceling out that term. All right, so this is, for those of you who are double E's, this is like IQ, right? In phase, and this is quadrature sort of detection, okay? So for each of these, we do a low pass filter of the data, okay? So we're basically sort of essentially smoothing the waveform that's coming in, and then we pass it into ADC, which is the analog to digital converter. And this is sort of like the bread and butter of like all of modern society, right? I mean, without ADCs, you wouldn't have the internet or anything like that. Like you got ADCs. Nowadays, everyone has an ADC, right? 20 years ago, no one would be carrying around ADC. Now you're all carrying around ADCs and DACs, right? Basically, this is taking like your images and converting it into digital, right? So it does two things. ADC actually does two things. It samples your data, right? So that's what we talked about, and it quantizes the data. Okay, so we're not really going to talk about quantization in this class, just because it's sort of out of scope. So for this class, it's more just sampling your data and it's quantizing it so it can store it as numbers. Okay, so when I talk into here or into here, so there's an ADC here, there's an ADC here, right? It's just taking my voice and taking my video. It's basically capturing the light or the sound, and it's converting into a number, right? So it's got to sample it at some rate, and it's also got to take some voltage level and turn it into a number, which is the quantization. So that's basically what it's doing. So MRI has that as well. We have some analog signal coming out of the RF coil. We need to measure the voltage. We sample the voltage and we quantize it. And then that gets stored as a number. Okay, so I think we're going to stop there for today since we're end of time. So any questions before we talk a little bit about project 2? Go ahead. Okay, good. Thanks for reminding me. Okay, so what I'm going to do now is I'm going to switch gears. Let's see, hopefully this works. Okay, good. Okay, so this is project 2, and I think these are all the details. So I'm just going to just go over some highlights and then open it up to questions. So essentially the bottom line is, in general, for most groups, you just keep the same group members, but there is an option to switch if you need to, but just talk to the TAs. Essentially, if you went live for CT, you'll go recorded for MR, and if you went live and vice versa, okay? So you just switch. I think I increased this. You could have a 10 to 12 minute presentation simply because we have a little more time during the final exam period. So you don't have to go this long, but certainly you can if you want to. We suggest 12 content slides. You can do more or less, but that's just a general recommendation. There is an initial proposal that is due similar to CT. It's going to be slightly different this time because from experience, we found out that since MRI sort of has a much bigger scope, one of the main things I'm doing is from the time of your initial submission to the approval, I will take a look at your proposal and I'll say, this is probably too hard, or, or someone else is doing it, or I don't think you should do this because, or maybe you need to expand the scope. So the idea is you have a chance to get feedback such that by the time you finalize your project, you know that it's something that, if done well, has a reasonable chance of scoring well in terms of the evaluation. I don't want people to spend a lot of time on things that are not going to score very well. Okay, so take advantage of that to get feedback. Typically, there can be anywhere from your first proposal can be like, yeah, that's great, good job, or else there might be 2 to 3 back and forths. Okay, so it's really meant to help you hone in on a project that you can do and will cover, sort of meet some of the scoring rubrics. Okay. And this year we're going to use Gradescope, which I've never used before, so we'll see how that works. Usually it's done by email, but the TAs have convinced me to use Gradescope, so we'll see how well that works. So yeah, I mean, there's just things about recordings and like just make sure we can see you on the recording, and also don't have your profiles overlap your presentation. So there's just like little logistic things there. Okay, so I think the main thing is that I would just want to stress is that, and right now I think Professor McVeigh is finalizing the grading for Project 1, but just some initial feedback, which is sort of relates to why we're giving you some more detailed feedback here, is it is important to and some of the feedback you'll get from me will be, I will really sort of emphasize connection to course content, right? Essentially, and where the biggest example of where it's easy to sort of go away from course content is, deep learning and machine learning, right? So if a presentation is 12 minutes long and 11 minutes of that is me learning about GANs and UNet or something, then I didn't have to take this course to do that, to listen to that presentation. So just be aware that that will tend not to, you'll in the scoring rubric, that won't do as well in terms of course content relevance, okay? So make sure that you sort of, if you are doing deep learning and machine learning, then we expect like, okay, here's something MRI specific about that, which we had to adapt, or here's why this matters for MRI, okay? This is something that you wouldn't be able to do if you, so the thing is, you can ask yourself the question, can the presentation be understood without MRI course principles? Okay, if you could understand the presentation with knowing literally nothing about MRI, then you probably would want to increase that connection. And then also the level of difficulty, it should have been 15 points for Project 1, but that's just sort of oversight. So the level of difficulty is now higher at 15 points. And so all that means is typically the projects that tend to do better will have like some simulation or some calculation or something that is a little bit above and beyond what's covered in the course, okay? So that's just general guidance as to what to look for there. And then there's just also lots of general things like do not spend too much time on things like, we don't expect 3 minutes about cancer, okay? Like if you're doing something, this is an MRI project, so don't tell us things that aren't sort of really advancing your case. Also, don't spend too much time just rehashing what's in the slides. So if 4 out of your 12 slides are basically course slides, then you're really not making the case for your own project. So really try to do the best for your own project. Show us what you did. The best projects will tend to explain very clearly, this is, here's some background, but here's what we did. We want to see what you did, okay? And also show, don't tell. Use PowerPoint, use animations, use whatever to show it. Like if you have a slide that's just text and you're just reading it, then you're not really using. I mean, although there are presentations like that, then that is just harder for us to get a sense of what you're doing. These are some examples from 2021 that I think are good examples, and so you might take a look at those. Is there just one there? Okay, well, it's on the YouTube channel, so you can look at that. There's lots of projects, so you have lots of room to do those projects. You can also, if you want to do some of a more guided experience, we used to have sort of final projects that were more sort of guided. And so there's one on echoplanar imaging and parallel imaging. These would certainly be of a level of difficulty that would do well. So you can, if you want to just follow one of those, you can certainly follow one of those. And then there's lots of resources online. This is just, some examples, but certainly you can use anything you want to sort of figure out your project. Okay, so this is just some things that I know about, but there's certainly much more. Okay, so that's just some general comments. If you have additional questions, you can ask them now or post them via email or to Piazza, and we can address them then. Okay, anything else? Yes. For project 1? Oh, right. Okay. So let's see. What did we decide? Okay. So they are due next Friday. This Friday, right. So I'll start looking at them over the weekend, right? So basically Saturday, I'll start looking at them. And then I'll start sending, I'll have Katie show me how to use Gradescope on Saturday. And then I'll start giving feedback, and hopefully that'll go well. And then hopefully, so then we want to have everything done by Wednesday at 5 p.m. so everyone can go on vacation and not have to think about it. Okay, so that's basically from Saturday to Wednesday, there's time for back and forth. Okay, any other questions? Okay, great. Yes, question. Yeah, I think, as I said, I think Professor McVeigh is sort of finalizing that. So hopefully in the next day or so. Yeah, I can't guarantee you, but that's sort of the timeline we're looking at. Yes. Okay, great. So if no other questions, we'll conclude for today, and we'll see you next time. Thanks. And I'm here to answer questions about homework or anything else.